So let me start my talk. This picture depicts what a static code analyzer for security does. So before I go ahead, and I'd like to ask, how many people have used the static code analyzer for security, or so what's called like SAS2, S-A-S-T? Okay, not so many. So I'll give a more detailed introduction on what it does. So here it shows such tool, which is called, I use the example of 45 SCA or HP 45 SCA, which is a static analyzer. It takes the input as its input source code, and it outputs a list of vulnerabilities in the source code. So the name of this analyzer suggests that its main techniques is static analysis. So let's look at the details of its output to get a better understanding what we can gain from this kind of tool. So this area highlighted in red shows a summary of the issues reported by the analyzer. For example, there are 13 critical issues, and 3 of them are cross-site scripting vulnerabilities, and 1 JSON injection, 1 SQL injection, and 8 privacy violation. So when you highlight one of the vulnerabilities, for example, let's click on the second cross-site scripting, then we can see the details of this vulnerability. So this area gives the taint traces for this vulnerability. The taint trace starts with a taint source, ends with a taint sink, and as well as the intermediate nodes that connect the source to the sink. So when you click on any of the node in the taint traces, it presents you the source code that the source location, so you can study why there is a problem, or you can say, oh, this report is actually not a problem. My code is correct, so you can mark it as false positive. So you can make notes at this area. So basically, this screen shows a GUI tool that presents and allow a user to analyze the results of security analyzer. So the general structure, because this kind of tools, security analyzers, use a static analysis. So it has a general structure that's similar to most compiler. For example, take the example of HP 45 SCA. It has a bunch of front ends, and each front end translates source code into a common representation, which I call normalized syntax tree in this talk. And then it has a backend. The backend is actually a collection of different analyzers. Each analyzer is designed for finding a set of vulnerabilities. So in my talk, I just give the example of taint analysis, which is done by the taint analyzer in SCA. So I think for people here, this probably invoke a diagram that LLVM provided as language independent services. So I want to emphasize here that there is LLVM has one more component than a typical security analyzer. That is the backend, because for security analyzer, we don't generate object code, so there's no backend. We don't normally transform the source code, so there's no transformation. but they share most of the common components. So here, I want to point out two important differences between a compiler infrastructure like LLVM and a security analyzer. The first one is the goal is different. The goal of a compiler infrastructure is to generate correct, smaller, and fast code, object code. The goal of a security analyzer is to present developer or security auditor the vulnerabilities in the source code. The second difference is a security analyzer doesn't have the component which is called the backend in a normal compiler. So the question that we asked ourselves was, if the LVM bitcode could be converted to a common representation which is closer to the source code, so that our security analyzer, like Tint analyzer, can directly analyze this intermediate representation and report vulnerabilities to our users. Why we ask this question? Because this is beneficial to both LLVM community and to security analyzer community. For the LLVM, this is a new application area which doesn't affect any existing applications. For security analyzer, we can add support to our security analyzer with minimum effort or even free for the languages that we don't currently support or we didn't support before, for example, Objective-C and the new languages such as Swift and all the other languages. Because there's a slide in the last year's LLVM development meeting. Vikram listed 22 different languages which can be compiled into LLVM. That means if we can do this, then we can gain the benefit for our application analyzer basically for free. So in order to demo that this approach actually works, so this is what we did for our Objective-C support. So we modified or we patched Clang so that the Clang generates a richer set of debugging information which can be used to convert the LVM bitcode into a high-level representation that we can use for security analysis. So as I mentioned before, because LVM has becoming a common infrastructure, if each front end add this special debugging flag, then this will open a door to another application area, which is security analysis, which is relatively new to the LLVM community. And I think this is good for both communities. A side benefit is that this enables the security analysis across different languages. This also comes for free. Okay, so why we cannot do this with the current implementation? Because there is a mismatch between the requirement of a Tint analysis and the information provided in the LVM bitcode. I'll explain what the mismatch is. So this is the code that showed before. And this code comes from iGoat 2.1. This function is a tent source. So tent is untrusted data. The places in source code where tent enters your program are tent sources. And the places where tented data, the use of tented data violates some security violation or security policy, tent sinks. And the tent sources and tent sinks are connected by intermediate nodes. In this case, it's connected, the tent flows from the source to the sink through the file contents variable. So how we identify tent sources and sinks? We study different APIs because nowadays, non-trivial function is always written such that it calls different library functions. And the library functions provides basic I/O support and the support to run any command on the operating system or any platform. So almost any sources and sinks are function or library APIs. And in doing source code security analysis, we match those library functions, which we identified as tent sources and tent sinks, against their function signature. And so we feed this knowledge into our analyzer by declaration. So this gives an example to show how we tell our analyzer which function is a source, a tent source. For example, it says node type. So basically, this declaration says if there's a code, if there's a code pattern in your program that matches this function call, whose class name is NSString, whose method name is init with contents of file, and the value is a return value. If there's such function call, we should mark a tent source at that location. There are also other information. For example, this tent source might be used to do command injection or path manipulation or do cross-site scripting attack vulnerability. Also, there are other attributes which I don't display here. So this is the function signature that we need in the source code in order to present the useful information back to a user. With that declaration of a tent source, so when we see this function call, we know this function, this function matches that call, so we can generate a source in our analyzer. The same thing happens for sink. Without sources and sinks, we cannot do tent analysis. It's very simple. So now our goal is to gain the source information from LLVM code. And this is what we can get from the current LLVM implementation. The first line shows an example of function definition, and the middle shows the LLVM bitcode of the function. If you look at it carefully, you can see the parameter type and the return type of the source code function are not distinguishable at the LLVM code. Both integer and unsigned integer are transformed into I32. However, LLVM has the metadata, debugging information metadata. This metadata describes what a function does. And there's API calls, API of the metadata which we can utilize to regain the information of the source code. For the previous example, for the convert function, for example, we can get the named metadata. From there, we can get the metadata of that function. And from there, we can get the type of that function. And from the type of that function, we can get its return type, which is int, and its parameter type is unsigned, then we can restore this information. However, if there's a code like function declaration extern, then we're out of luck because there's no metadata that describe what this convert function is in the source code. Why? Because the metadata emission process is embedded in the code generation. There's no code generation for API declarations, so there's no metadata for those functions. From the compiler's point of view, this is an efficient way to implement debug information. But this is not sufficient from a security analyzer point of view. So in order to utilize the huge functionality that LLVM provides to us, we come up this idea we solve this idea by doing the following. So we decouple the metadata emission and code generation, and control the to control the metadata emission process by an extra debugging flag, which we call -g src. And then if you run Clang with this parameter, with this argument, then we get extra metadata that describe what the API function is. The top part of this slide shows what the declaration looks like for that function in LVM bitcode, and the bottom part shows its associated metadata. Also, extra information about this function can be regained. For example, its type signature, although Objective-C doesn't use types for its method signature. And also we can know, all those types are actually, there are some types are equivalent. For example, the NS string encoding, NSU integer are actually long unsigned integer. So with all those extra information, then we can restore the function signature that we required to do security analysis. This shows how we use our enriched debug information to restore an IR, which is much higher level than LLVM, looks like source code. So this is our solution to the question that we asked. This is actually a very small change to Clang and to the front end and LLVM. This work we only did like the entire patch only has 543 lines. Plus a little verifier, which verifies all the source level information is correct in the bitcode. And so now we're upgrading to 3.5 because 3.5 has some change in generating the bitcode and debugging information. So again, this is my hope. Because I believe this will open the door to a new application area for the LLVM infrastructure. And also, the security applications or security analyzers can benefit from the rich functionalities that's available in LLVM. Okay, thank you very much. And any questions?
In your example, you showed compiling with -0. what happens if you were to pass -01 or higher?
It doesn't affect the generation of the extra metadata. It only affects optimization that's exercised. For example, if you patch -02, it generates shorter code, but it still has the metadata.
But how does it affect being able to take your source and identify?
Okay, it has negative effect. Yeah. So for the better quality of IR, which is closer to source level, I would suggest use -00. Well, we didn't measure it quantitatively.
Sorry, can I give you the microphone?
Build time, right? If you took the bitcode, you could feed it back both into security analysis and code generation. Save build
time. So at the very beginning, you mentioned that the tool has false positives. What is the rate of false positives on large non-trivial programs if you tested it?
Oh, that's a good question, because false positives are a major issue in applying static analysis for security, because it depends on how you design your analyzer. For example, most taint analyzers nowadays are not path sensitive, which means if you have any check guarded by nested if statement of the guards across different functions, you will get false positive.
So I come from the refactoring community, and I certainly need parts of the AST, and I tend to do them much more at the front end. Did you think at all about trying to make or propose a consistent interface to the different language front ends that would get you the information you need? And do you think that would be a better way long-term for LLVM?
Yes. Yes, actually we thought about that, and I think I agree. Yeah. Because LLVM is is a low-level representation. It's not ideal for high-level analysis. Actually, if we have some common representation which is closer enough to abstract most source-level abstracts, which can benefit everyone.
So you showed that you do this pattern matching on what functions are called to find sources and sinks for your taint analysis, but I'm not completely sure why you don't do that on IR level. So all the information, like, okay, I call this class, this function, is also in the IR level, and now you show, okay, I add this high-level information in the Clang backend for 500 lines of code. I have 21 front ends, which is like 500 lines times 21. And otherwise, I just need to, my taint analysis has to match IR. I don't get the point why you don't do that.
There are two major reasons. The first reason is that matching IR is not preferred by most users, because when you give a user a security analyzer, different users have different security policy, and they want mark certain functions as taint source from their point of view. So if it's not practical to expect all your users know LLVM IR. So the most way for them is to mark the source language, which is basically it's a user requirement. The second reason is that at the IR level, you cannot the IR itself is not analysis friendly for high level. For example, like the information I showed is available through the enhanced metadata, but they are scattered around in the LVM bitcode. When you write an analyzer, for example, if you want to write a visit pattern, it's very complicated to handle all this information together. But if you transform the IR, LLVM IR into another IR which is more convenient to analysis, I think that's a good way.
I have a question on the taint analysis algorithm you're using. From the slides, you show like how the annotations, you annotate the functions as tainted sources. Looks like you are marking every file, the file content, as thinking. Would that give a lot of false positives? Because I imagine these files are like generated by the internal system rather than from outside. So I'm curious about what your algorithm is on reducing the false positives.
Okay, I can explain more on that. So the taint sources and taint things are marked by human, by our study to different library APIs or framework APIs. What's the function of the analyzer is to connect sources to things. In this example, because this particular example has a very short intermediate node, but in actual code, the connection can be very deep through multiple function calls. If you look at the code, you can get lost very easily. So that's the real power of static analysis. And in order to get a precise result, we need context-sensitive analysis. We need path-sensitive analysis. But when you add more functionality in, the scalability of your analyzer becomes very poor. So sometimes it's an engineering trade-off to get rid of some context information to make your scanner to analyze big code base.
I wonder if the speed is a concern of the tool. So how fast or how slow is your tool? And if it is a concern, then do you do anything to improve it?
Sorry, what's is the tool?
Question was speed.
Speed.
How fast or how slow is your
You mean
analysis?
is the security analyzer?
Right.
Compared to LVM, it's very slow. For different reasons. First, our analyzer is written in Java. Java is slower than C++. So the second reason is they do different things.
So going back to false positives again, I'm sorry. On large code bases, it's a huge problem, right? Because the kind of noise that you get running security analyzer on your code base. So I was wondering if you have any ideas as to doing source annotation to reduce the number of false positives that your tool is generating. So you can maybe, I don't know, annotate the source itself, or maybe have some kind of mechanism where it says that, okay, don't worry about this problem, I know that it's correct.
Yes. I think the annotation is used by some of the security analyzer vendors, but we don't use it much. Instead, we allow user to audit the issue during the auditing process. They can mark if an issue is false positive. So when they scan their code again, those issue marked as false positive won't show up again. Because that's also a trade-off. Because annotating code actually requires a lot of effort. Especially, you have to have some people who know the code very well. Most security auditor cannot do any annotation on source code. Only developer can annotate. But there is miscommunication or missed connection between developer and the security auditor. That can be a huge barrier in using annotation.
So is the patch public? Do you plan to make it public?
Yes, actually, we initially thought about submit the patch to LVM developer team, but when we started looking into the process, we found we need to do more testing and to do code review and because we modified the metadata and some test cases has to be modified in order to pass, and then those required some extra work. And so we just didn't put much effort to that. Another reason we didn't do it is because we asked the opinion in LVM developer mailing list, and the general consensus I remember I got was this was not required. This was not needed in terms of a compiler, and which I agree because the compiler has a completely different goal. That's to get smaller code size and faster object code. And the information about API functions is not used. Why do we bother to generate metadata for them? So I hope that by showing this their practice, or by showing their benefit, and they can accept our patch too.
Okay, let's thank the speaker again.
Thank you.